by popular demand, more bonus multiple choice review questions before the test. Now, hopefully you never ever feel like multiple choice questions that I give you look like this, and you're like, "Whoa, Mr. G, don't do that to me." So we're going to look at 10 problems. I believe it's 10. Most of them are out of the book at the end of the chapter in the practice test. And I have one additional question that comes from the kind of test bank that I get from the textbook. So the first one we're going to look at. A study of road rage asked separate random samples of 596 men and 523 women about their behavior while driving. Based on their answers, each respondent was assigned a road rage score on a scale of 0 to 20. Are the conditions for performing a two-sample t-test satisfied? Okay, so regardless of what type of test we're doing, whether it's two-sample, one-sample, t-test, z-test, interval, confidence interval, or not interval, confidence interval, test, or a confidence interval, the three conditions are always going to be the same: random, independent, normal. Now, this question in particular here, what are we trying to do? We have scores 0 to 20. We're trying to separate maybe men from women to see if maybe they have different road rage scores here. The scores are going to be more of a mean level score, so that's why they're talking about a T test instead of a Z test. So first off, random. Do we have random samples? Yeah, we're good. Independent condition. Can we assume that the population of men is greater than or equal to 10 times the men's sample size of 596? So basically, are we saying, can we assume that there are more than 5,960 men? Yeah, and can we assume the same thing must be true about our women, that there are more than 5,230 women? I believe so. So it seems like the random and the independent conditions both look like they've been met here. Now, since we're doing a mean level test, when we check the normal condition, do we know that the populations are normal? No, they didn't tell us that. Do we have large enough sample sizes for the central limit theorem? Oh, we do. We have some pretty large sample sizes here. So we can say, yeah, central limit theorem really works here. So now let's run through all our choices. Are the conditions satisfied? Let's start with the yeses here. Yes, we have two independent random samples and large sample sizes. Well, there's our random, there's our independent, and our large sample sizes is basically our central limit theorem kicking in here. So I would say it's got to be E, but let's knock out the other choices just so we feel confident with what we're doing. Yes, the large sample sizes guarantee the corresponding population distributions will be normal. Okay, but it didn't talk anything about the random or independent conditions. So they talk about one, but not the others. No, we don't know the population standard deviations, meaning, do we need to know what sigma is for both populations? No. Road rage scores in a range of 0 to 20 can't be normal. Why not? Just because, are they trying to confuse the central limit theorem with these scores? It has nothing to do with the central limit theorem. It's not our sample sizes. Maybe we have independent random samples. Okay, cool. But we need to look at the data to check normality. Now, they didn't actually give us the data for the 596 men and the 523 women, but we don't need to look at the data because these sample sizes are big enough for the central limit theorem. Now, if these were both under 30, then yeah, we would need to look at the data. So no. So yes, the correct answer is in fact E. Everything checks out here. There are our three conditions. Number 2, 35 people from a random sample of 125 workers from Company A admitted to using sick leave when they weren't really ill. 17 employees from a random sample of 68 workers from Company B admitted the same thing. A 95% confidence interval for the difference in the proportions of workers at the two companies who would admit to using sick leave when they weren't ill is... Now, since we're doing a two-sample proportion problem here, and they told us we were doing proportions in the difference in the proportions, so we're using the P1 hat minus P2 hat plus or minus Z always for proportions, square root. Now here's the thing you got to remember. In one case, we had that special P hat, which was when we added together all our successes, our quote-unquote successes, and divided it by the sum of our two sample sizes. did we use that for confidence intervals or for hypothesis tests? Because it was one or the other. And this is one thing you're really going to have to straighten out in your head. We use this for hypothesis tests, and we're doing a confidence interval. So our square root actually uses the individual p1 hat, then times 1 minus p1 hat all over n1, and then the p2 hat times the 1 minus p2 hat all over n2. Okay, so my differences apparently is 0.03, but we don't actually have those values here. But if we looked at here, 35 out of 125. 35 out of 125, my calculator gives me 0.28. And 17 out of 68, I know is a fourth, so that is 0.25. So yes, the difference between 0.28 and 0.25 is 0.03. So now let's look at z's. We know we're going to have to use a z-score, which uses inverse norm. Inverse norm, using a 95% confidence interval, means we have 0.025 in the tail. There's no degrees of freedom with normal distribution. That's only t. And if you put that in your calculator, you should get 1.96. So in A, there's no z-score there. It's not it. This uses 1.96. This uses not 1.96. If you use inverse t, you would get 1.645, I believe. Or maybe that's for a 90%. That's probably for a 90%. So they're assuming you're going to put in 0.05 because you didn't realize you're only supposed to do one tail. So that's what it is. If you use inverse norm 0.05 for both tails, then you get that. And then we get that again. So we're down to B and D. So now everything else has got to come from the square root. Now if you look here, that's one of our p hats there. And here's the other p hat. Okay, so this looks legitimate. There's our sample sizes, 125 and 68. Now down here, notice these match up. They're the same. They're using that pooled p hat value. That's a combination of p1 hat and p2 hat. And we said we don't use this for confidence intervals. We use this only for hypothesis tests. So D is not the correct answer. B better be, and it is. It is the correct way. Now, there will be some multiple choice questions like this on the test and on the actual AP exam where you just need to verify which formula would you use. Okay? You don't actually have to now do it and figure out the confidence interval. You just need to verify which one has all the numbers plugged in the right spots. The third one, technically we're skipping number 3 in the AP practice test at the end of the chapter. I didn't really like it, so I just crossed it out. A quiz question gives random samples of 10 observations from each of 2 normally distributed populations. Tom uses a table of t distribution critical values and 9 degrees of freedom to calculate a 95% confidence interval for the difference in the 2 population means. Janelle uses her calculator's 2 sample t interval with 16.87 degrees of freedom to compute the 95% confidence interval. Assume that both students calculate the intervals correctly. Which of the following is true? Now, one thing I notice here, it says, assume both students calculate the intervals correctly. And then E says Janelle made a mistake. They're telling us, even though it's saying assume that they did it correctly, we're going to go with that assumption. So E is automatically wrong. Now, Tom, he used degrees of freedom that were 9. We just turn that into a colon. Tom, 9 degrees of freedom. And he had 10 observations here. So he's using the sample size minus 1 to get this. Now, Janelle, on the other hand, her degrees of freedom were crazy looking, a decimal. How did she get that? She must have been using that crazy Satterthwaite formula that the calculator uses. Okay? And that's always going to give you more degrees of freedom than you would get by taking just the smaller sample size minus 1. Now, they're wanting to compare intervals here. That Tom's confidence interval is wider, Janelle's is wider, they're the same, or there's insufficient information to determine which interval will be wider. Now, here's the thing here. The calculator will give a narrower confidence interval with this more precise degrees of freedom. Tom's degrees of freedom was a more conservative estimate, and being more conservative means you were going to have a wider confidence interval as a result. Now, it shouldn't be too much wider than using the calculator Satterwothy formula, degrees of freedom, but there will be a noticeable difference. So the answer is A, check. Tom's confidence interval will be wider because it's using the more conservative degrees of freedom value. Now, all of this we're going to get to use twice. And let me see. Yeah, I repeated it on the next one. So this is very similar to the second one. We just need to match up the correct formula here. Now, let's run through this. Researchers wish to compare the average amount of time spent in extracurricular activities by high school students in a suburban school district with that in a school district of a large city. The researcher obtained a simple random sample of 60 high school students in a large suburban school district and found the mean time spent in extracurricular activities per week to be 6 hours with a standard deviation of 3 hours. The researcher also obtained an independent simple random sample of 40 high school students in a large city school district and found the mean to be 5 hours and standard deviation to be 2. Suppose that the researcher decides to carry out a significance test of really are the two means the same between a city and a suburban school versus a two-sided alternative that basically that they are not the same. The correct test statistic. So typically we would do t equals x1 bar minus x2 bar minus mu1 minus mu2 over square root s1 squared over n1 plus s2 squared over n2. This will be 0 because this is really coming from our null. And they're saying, is there a difference between these two and according to our null? No, there's no difference. So that's where we always get our 0 from. They did tell us that one mean was 6 and the other was 5. So all of these check out. And all of them have a minus 0 attached to the end. So everything's good so far. The difference is going to come in our denominators. So we need to square our two standard deviations of 3 and 2. So, hey, they didn't square them here. That's not it. Hey, they did square them. Cool. And did they divide them by the appropriate sample sizes? So the 3 standard deviation was for the 60, so that checks. And this was for our sample of 40. There. So that checks. So this one looks like it's legit. But let's make sure it is legit by crossing out the others. This down here, there's no square root. And 9 and 3? How'd they get 9 and 3? I mean, 3 squared is 9, but 3 isn't 2 squared. So that's not really adding up there. This one, nope, look, they didn't square them. Nope. This one they did square, and the 60 and the 40, holy cow, these two look like they match, right? But do you see the difference? This one says z equals, and we are specifically looking for a t-score because we are doing a mean level problem here. So B, ping, is the right one because it says t equals. Tricky ticky. Number 6 says the p-value for the test is 0.048. A correct conclusion is 2. Now they didn't give us an alpha value up here, but in each problem they state the alpha value is 0.05. Now, our p-value is less than an alpha of 0.05. So we are saying the p-value is too low, the hoe gotta go, which means we are going to reject the null hypothesis. So A says, fail to reject. Nope. B, fail to reject. Nope. C, fail to reject. No. D and E do both say reject the null at the 0.05 level. Now the main difference here is where the not is located. D says there is not convincing evidence, and E says there is convincing evidence. Well, since we are rejecting, we are saying there is convincing evidence of a difference in the average time spent on extracurricular activities by students in the suburban and city school districts. We're always trying to conclude the alternate hypothesis, and the alternate would be that there is a difference. So there is evidence that there is a difference. So the answer would be E. And bing, double check, it is. Next up, at a baseball game, 42 of 65 randomly selected people report owning an iPod. At a rock concert occurring at the same time across town, 34 of 52 randomly selected people report owning an iPod. A researcher wants to test the claim that the proportion of Ipod owners at the two venues is different. A 90% confidence interval for the difference in population proportions is negative 0.154 to 0.138. Which of the following gives the correct outcome of the researcher's test of the claim? Now, since we're always doing a difference here, we're always looking for a particular number in our confidence interval. And we are looking for 0. Is 0 inside this interval? And you would say, yes, 0 is inside there. From a negative to a positive, it has to cover 0. So this says, since the confidence interval includes 0, includes 0, includes 0, since the confidence interval includes more negative than positive, this is sounding odd. We don't really care if there's more negative than positive, so this one's probably more than likely wrong. The researcher cannot draw a conclusion, but we can draw a conclusion here because we're looking for 0, so that's going to tell us yes or no. So let's see what the differences are here now. So if 0 is in there, we are basically saying that what? That there's 0 difference, right? So this says the researcher can conclude that the proportion of Ipod owners at the two venues is the same, that there's 0 difference. Well, this sounds good, right? So let's put a little check mark here. This one's sounding pretty good, but let's make sure we can eliminate the other two. The researcher can conclude that the proportion of Ipod owners at the two venues is different. Well, no, if 0 wasn't in there, then we would say that they are different. The researcher cannot conclude that the two venues are different. So this is saying the researcher could conclude that they are the same. This is saying he cannot conclude that they are different, which is kind of like saying the same thing, right? It's almost like a double negative. Now, both of these sound legit, but which one's more legit or too legit to quit? Hey, hey. It's a musical reference there if you didn't understand that. I believe MC Hammer, if I'm not mistaken. The main thing you need to know here is to remember, what did we always write our conclusion in reference to in a hypothesis test? We always said that we did or did not have enough evidence at the whatever alpha level to conclude what? We always talked about it in reference to the alternate hypothesis. Okay, and the alternate hypothesis, well, first the null would be that they are the same. They have the same proportion. That the proportion, where are we at a baseball game, would equal the proportion of Ipod owners at a rock concert. And the alternate would be that they're different. So this is what we're always trying to conclude. Do we have enough evidence or not to conclude this? Well, this one's more in reference to the null. And we can never conclude that the null is true. That's why we never accept the null hypothesis. We will only fail to reject it. So technically A is not right. It's referring to the wrong part of the hypothesis. Now C, check, is the correct one. Since 0 is in there, we would fail to reject. So we do not have enough evidence to conclude that the two venues are different. Next up, simple random sample of 100 is taken from population A with proportion 0.8 of successes. An independent simple random sample of 400 is taken from population B with proportion 0.5 of successes. The sampling distribution for the difference A minus B in sample proportions has what mean and what standard deviation? So we're dealing with proportions. We're taking A minus B here. So the mean of sample proportions, we're doing sample proportions. So of A minus B and the standard deviation of A minus B. Well, this was just the difference in the proportions. So this was 0.8, and they said this was 0.5, which makes, hey, 0.3. Does that get us anywhere? Hey, at least we get to cross out 1. They say negative 0.3. Now, you'd get negative 0.3 if you would have subtracted the other way, which is obviously wrong because they specified which way to subtract. The standard deviation, ooh, this is the fun one. PA hat times 1 minus PA hat, all over the sample size of A, which was 100, plus, oh, well, here, I don't want to mix these up. Let's go ahead and write out the full formula first, in A. And then P hat B times 1 minus P hat B all over in B. So now let's plug in our numbers. This would be 0.8, this would be 0.2 over 100, plus 0.5 times, well, another 0.5 for the failures there. And then 400 there. So now punching this in, you do not need any extra parentheses when typing this in. You can just type in, once you hit the square root, 0.8 times 0.2 divided by 100 plus 0.5 times 0.5 divided by 400. Enter, and I get 0.04717 for sig figs there. And which one is this matching here? That was obviously a match. That isn't it. That isn't it. That isn't it. That obviously wasn't it before. Now, notice that is the correct standard deviation. It's just using the wrong mean. So C, pling, is our correct answer. So you're going to need to remember these formulas for mean and standard deviations. Now, this one wasn't any kind of confidence interval or hypothesis test problem. This was more the beginning of the two sections, where we did just individual probabilities, and some of you would confuse them with confidence intervals and hypothesis tests. Next up, how much more effective is exercise and drug treatment than drug treatment alone at reducing the rate of heart attacks among men aged 65 and older? To find out, researchers perform a completely randomized experiment involving 1,000 healthy males in this age group. Half the subjects are assigned to receive drug treatment only, while the other half are assigned to exercise regularly and to receive drug treatment. The most appropriate inference method for answering the original research question is... Now, this is where I told you before, whenever you do a free response question, you always have to write out the formula without the numbers plugged into it. Or you have to identify the problem you are doing by name. Now this is focusing on the names. So this is something we haven't really talked about that often, but there will be questions like this. Now, I'm not expecting you to know the names, but I think we can reason through which one has to be the right one here. So work with me here. Number one, are we dealing with one group of people or two groups of people? They said we do have one group of 1,000 people, but we are splitting them up. Okay, so we don't have one sample. We have two samples. So check, 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 check. Now, are we talking about, well, before we get to Z and T, are we doing proportion problems or mean problems? Well, are we calculating the mean heart attack rate? No, we're just trying to figure out the proportion of heart attacks. You know, out of the 500 who do exercise and drug treatment, how many of them, not the mean amount of them, but how many of the 500 that did both things had a heart attack later? And then how many of the 500 that just took drugs alone without exercise? How many of them had heart attacks later? So we're just calculating proportions here. So these aren't mean problems at all. So that means these two are out. So we're doing a two sample, obviously a Z, but are we wanting to calculate an interval or a test? And here we're just meaning, are we going to calculate a confidence interval or perform a hypothesis test? Now, it says how much more effective is this treatment compared to that treatment? Now, doing a hypothesis test, our null hypothesis would be that the two groups would equally have the same amount of heart attacks versus they would not have the same amount. Okay? Now, this says how much more effective. Is this going to tell us how much more effective? No, this is just going to tell us if they're different or not. It really doesn't give us specifics about how much more effective it is than it is not. Now, a confidence interval is going to give us specific numbers, right? And if let's say we reject the null hypothesis here, it's going to give us actual numbers. You know, maybe it's anywhere from 13.45% up to, and I'm just making these numbers up here, maybe all the way up to 23.45%. This is giving us how much more effective that we're looking at. It's between this and this number. So we should calculate a confidence interval to determine how much. Now, if they changed a couple words here, it would turn into a hypothesis test. So let's say they changed the wording around to this. Here, let's just do this. Is exercise and drug treatment better than drug treatment alone at reducing the rate of heart attacks among men aged 65 and older. If they did it this way, then I would say, yeah, they're setting me up here for a hypothesis test. They're just wanting me to know are these two things the same or are they different? So let me double check just real quick. Boom, it is confidence interval. Man, I'm going to ace this. I'm going to ace this test. I don't know about you guys. I'm going to ace this thing. All right, next question. Researchers are interested in evaluating the effect of a natural product on reducing blood pressure. This will be done by comparing the mean reduction in blood pressure of a treatment, a natural product group, and a placebo group using a two-sample t-test. The researchers would like to be able to detect whether the natural product reduces blood pressure by at least 7 points more on average than the placebo. If groups of size 50 are used in the experiment, a two-sample t-test using an alpha of 0.01 will have a power of 80% to detect a 7-point difference in the mean blood pressure reduction. If the researchers want to be able to detect a 5-point difference instead, then the power of the test would be less than 80%, greater than 80%, still be 80%, could be less than or greater than 80% depending on whether the natural product is effective, or would vary depending on the standard deviation of the data. Now this is kind of relating back to the last chapter when we talked about power. And let me just remind you, power is the probability of rejecting the null hypothesis, and that's the correct decision. All right, so they're saying that there's an 80% chance that if we reject the null hypothesis, and that's the correct decision, and well, first let me write this. The null would be that the mean, how are we going to say this here? Mean of the natural product would be the same as the mean of a placebo, versus we want to show that the mean is more than using the natural product than using a placebo, okay? Or we could rewrite this in terms of a difference, that there needs to be a positive difference if I subtract these two groups. Now, there are infinitely many numbers that are greater than 0. They decided just to pick on a 7-point difference. Now, a 7-point difference is greater than 0, okay? And they're saying that if they did this with a sample size of sample size of 50 in each group, that there's an 80% chance that a 7% difference will be the correct decision to make. So, if they want to lower the 7-point to a 5-point, what would happen here? Have you guys kind of mull on this for a little bit. 80% chance that it's 7. The bigger this difference gets, the more confident we're going to be that we're making the right decision. The larger the difference gets, the higher and higher this thing is going to climb to be 100%. It's never going to be exactly 100%, but it's going to approach 100%. The limit will be 100%. So that means if we go back down towards 0, well, if there's only a 1-point difference, are we going to be that confident that we're making the right decision if we reject the null? Not as much, no. So our power should be less than 80% if we lower the point difference closer to 0. So I would say the answer is A, and we get A. Now, this is kind of an abnormal problem. I would not expect something exactly like this, but just to kind of keep you on your toes, there might be some stuff from previous chapters on this chapter test. Here's the last question. This is the one that's out of the test bank. Which of the following describes a situation in which it is safe to employ T procedure? So we're doing a mean problem, okay? Okay, let's see here. We got a sample size of 10 and 40. Both samples are moderately skewed. Well, this one's cool, right? Central limit theorem kicks in here. But a sample size of 10, that's pretty low. We can't use central limit theorem. And they told us that the sample is moderately skewed. All right, so they didn't say strongly skewed, but moderately skewed. Well, I don't know. That was kind of iffy. B, 10 and 8. Sample 1 is approximately normal. So hey, even though we have a small sample size here, if it looks approximately normal, hey, that one's going to be good. We're cool with that one. And ample, yeah, good job, checkers here. I guess ample is a word, so I guess spell check didn't automatically, oh wait, I gotta do the right color here. I guess they didn't see spell checker go, hey, what's this word supposed to be? Sample 2 is skewed right. Now they didn't say strongly skewed right, but we do have a small sample size here. So is skewness okay? I'll talk about something here in a bit. So this one seems, I don't know. Next up, 6 and 6, both samples are approximately normal. Okay, now if your two samples are approximately normal, even though they're fairly small, that's actually okay. So that looks pretty good. D, 35 and 40. Oh man, we've got central limit theorem written all over this. Both samples are approximately normal. Sweet, even gets better. Sample 2 has 2 outliers. Oh. CLT versus outliers. Does central limit theorem trump outliers? Or does outliers trump central limit theorem? That's a question here for D. It is safe to use T procedures in more than one of the situations above. Awesome. Don't you love these types of problems? Here's something you need to know. If, that is obviously not an F, if you were dealing with small sample sizes, and by small the book considers them 15. So if you're dealing with sample sizes under 15, definitely no outliers. And really, skewness is considered bad. You want your sample, if it's smaller than 15, to look fairly normal or, pretty symmetric looking. So, something like this, something that could reasonably look like a normal curve. So going back up top here, moderately skewed, change our color up here, moderately skewed with a sample size that's 10, this is saying that's not going to work. Sample 2 is skewed right, and it's less than 15, they're saying that's not really going to work. C, though, even though we do have two very small samples here of 6 and 6, since both of them are approximately normal, that's saying, yeah, that's looking okay. Now, to get back to this one, central limit theorem worked for both of these, and they are both approximately normal, sweet, but it said sample 2 had 2 outliers. Here's the thing. Outliers do have more of an influence than the central limit theorem does. Okay, keep that in mind. So this is a no-no. Even though we have a large sample size, and even though it technically looks approximately normal, it's not going to pan out here. So T procedures is safe in more than one of these? Nope. Just C. So double check, and we are good. Now this one's a little tricky because some of you asked me the other day in class, there was a specific example where something looked okay. We had a large enough sample size, but there were some outliers present. It is true that outliers do trump the central limit theorem. It is unfortunate. And here's where we can kind of reintroduce a term that I kind of skipped over a couple chapters ago, but I've mentioned it a little bit from time to time, and that term is robust. Okay, and let me go grab real quick out of the book the definition of robust. Okay, here's what I pulled out of the book here. It says the T procedures are relatively robust, which means it's okay to still do whatever procedure you're trying to do when the population is non-normal, especially for larger sample sizes. The T procedures are not robust against outliers, however. Okay, so outliers here means it's not robust, which means T procedures cannot really be used in this case. So that's a term you might see. I'm not going to put it in my tests, but you might see the term robust if you were to take the AP exam. Okay, so that's just for those people who are planning on taking that. Again, I wouldn't put any questions related to robustness on the chapter tests. That is all the problems. I hope you had fun. Good luck. I think I got 100%. I'm going to ace this bad boy. Hopefully you do too.